Hey everybody, today we're talking about 4-3 complex zeros and the fundamental theorem of algebra. So for your objectives, it's to be able to use the conjugate pairs theorem, which is basically if you have an imaginary root like negative 2i, then you'd also have positive because they come in pairs. And if you had something a little bit different, we'll get to it later, but if you had something like 3 minus 5i, then you'd have 3 plus 5i. We'll see that later on in the lesson, but they come in pairs. So your second goal is to find the polynomial function's zeros and to find the complex ones. So while we're studying this, in section 4.2, we found the real zeros that were degree 3 or higher. In this section, we do the complex ones that are 3 or higher. So that means it could be real or imaginary. So the real ones are the ones that cross the x-axis. So for your notes, a variable in the complex number system is called a complex variable. A complex polynomial function of degree n is in this form where it's decreasing down to a0, where the numbers are complex numbers and not 0 for an. An is the leading coefficient. The complex number r is a complex 0 if f of r is 0. Now, some quadratic equations have no real solutions, but in the complex number system, every quadratic equation has a solution, either real or complex. So like previously, like in other math classes, you may have just said no real solutions and you were done. But here we've got to figure out what the imaginary ones were. Carl Friedrich Gauss extended this idea to polynomials 3 or higher, and it's called the fundamental theorem of algebra. It's like the most important fundamental thing. Every complex polynomial function of degree n has at least one complex 0. So about the I squared and the I part, remember that I squared is -1. Also practice simplifying and expanding. What I mean by that, I'll put it up here. So if we have I squared equal -1, that means I was the square root of -1. And if we have I cubed, we can write that as I squared times I, which would be -1 square root of -1, but we would just call that -I. And then on I to the 4th, we would say -1 times -1, which is positive. And then once you get to that one, I to the 5th would be rewritten as I to the 4th times I, so 1 times I, so I to the 5th is I, and so on. So you're going to practice with those. You have this theorem that every complex polynomial function of degree greater than or equal to 1 can be factored into n linear factors, not necessarily distinct because of multiplicity 2, when it touches or bounces off. That is, every complex polynomial of degree n has exactly 1, which could repeat. For example, you might have one that's 4 minus I, and then in factored form it's x minus parentheses 4 minus I. Then you have to distribute or expand. Okay, so for the conjugate pairs, if you have r equal to a plus bi, then the complex conjugate is a minus bi. Notice the a stays the same sign, but the minus bi changes. So that's what I did here. when we said 3 stayed the same, and if this one's negative, that one's positive. Okay, looks like I have that corollary here. If it's of odd degree, then it has at least one real zero. For example, if you have 3 plus 5i, then you have 3 minus 5i, not negative 3 plus 5i. So you don't change the front. Every polynomial function can be uniquely factored into a product of linear factors and or irreducible quadratic factors. Those are ones that can't be reduced. That's what irreducible ones mean. So that was about a product of linear factors and or irreducible quadratics, kind of like a prime factor. Like a prime quadratic factor can't be reduced. Then I say, see example on finding a polynomial whose zeros are given, or use an example. We haven't been using textbooks lately, so if you want to refer to it or borrow it, you can. I'll show what I was talking about. So page 213. Example 2. Okay, so what we have for that one is finding a polynomial whose zeros are given, and there are a lot of steps. So basically, negative 4 plus I was given to be a 0, so that means negative 4 minus I also is. And then we write it with the, the part that had 1, we put the x minus 1. And then with these, we have to do x minus parentheses negative 4 plus I. So then you change your signs, and then you got to work it out. Same thing for the other one. So it is a bunch of work for that, but that's how you end up doing it. On number 20, it says find the zeros. That must have been book number 20, which is over here. You may want to label the front and back part while expanding to get the factors. If it's 6th degree, you can stop, but if it's on 4th or 5th degree, you need to expand all the way. So what I'm talking about is number 20. Here I have a 6th degree polynomial, and we were given I, 4 minus I, 2 plus I. Then you got to figure out, well, because of the conjugate pairs, I have negative I, 4 plus I, and 2 minus I. And then you start the step where you have A in front, and then X with all the minus all of these, basically. Then you got to expand and combine your like terms. Now, when you have I squared is negative 1. So I was saying this is the right side, this is the left side, and so forth. And then I was going to stop right there since it's 6th degree. So I know I'm not showing one yet from the Math Excel, but these do get complicated. Because in the T, it wanted you to continue expanding and get x to the 6th minus blah, blah, blah. So not just these 3 terms that are quadratic. Okay, so now let's move on to the actual problems. So I know this part is usually the most helpful for y'all. The answers are in line, and let's get started. So if you have a 0 that's I, then we think negative I, and if it's 9 plus I, we put 9 minus I. That's how simple that is. On this one, we're given 2I and 4I. Well, you don't just randomly make it -2, but you do make it -I and -4I. Again, this is about the conjugate pairs theorem for both of these. So those are like very quick. On this one, you have 5 plus I, so then you'd have 5 minus I. And this one's 6 minus I, and so you'd have 6 plus I. So again, 3 really easy questions right off the bat. And now you're on to number 4. Okay, so on this one you have 4 zeros because it's 4th degree. And it says 4 with multiplicity 2, which means you're going to have x minus 4 squared. It also says you have 6i, which means you're going to have x minus 6i. And remember we said it comes in pairs, so negative 6i, which means x plus 6i. Okay, so now what we need to do is expand this part, and that is going to be x squared minus 2 times x times -4. If I put minus here, I need to put plus here. I'm just going to put plus 2. Plus 2 of these products, which is -8x, plus 16. So I'm going to continue working with just the left. X squared minus 8x plus 16. Okay, so there's the left side. Now on the right side, we do x times x is x squared. Then remember, if it's plus or minus of the same thing, that would cancel and that would cancel because it's positive and negative of the same thing. And then this part is -6 times 6 is -36, and then it's I squared. Well, if you don't remember, telling you again, I squared is -1. So if you have -36I squared, we really change that to plus 36. So what I usually do is just write it as plus 36. Okay, so now you take your x squared times these. So this would be x to the 4th plus 36x squared. Now you do -8x times both of them. So -8x cubed minus 36 times 8, 288. And that one's an x term. And then, so we did 8x times this one and 8x times this one. Now we need 16 times this one and 16 times that one, which gives you 576. So once you're at that step, combine your like terms, bring down your x to the 4th, and then there's one x cubed term. Now there are a couple of, I put 36 squared, I meant 36x squared. You need to combine your -36x squared with your 16x squared. So positive 36 plus 16 really is 52. So that's plus 52x squared. And then this one doesn't have another term, so it's -288x. And this one you bring down 576. And that is what they have over here. So that's an example of the 4th degree. So the most important thing was when you had -36I squared, you change that to plus 36. And your 6I minus 6I cancels. Okay, now we need this one. Use the given 0, which is this one, to find the remaining zeros. Well, one of them is going to be 3 plus 3i, because we have to have the conjugate pairs. For the other, we just need to graph it. So we have x to the fourth minus 9x cubed plus 18x squared plus 54x minus 324. Okay, so there are my values. I can do 0 the graph. Between here and here is negative 3, so negative 3 is an answer. And menu analyze 0. Between here and here, 6 is a 0. So those two are real, and those two are imaginary. And so we had to do those. Okay, that's number 5. Number 6. Okay, 6 is one of the longer examples. What we start with is thinking about how we would factor x cubed minus 343. So you need to know about the difference of two cubes. Because I know you can do the cube root of 343. You do control up arrow. We want the cube root of 343 is 7. So this is like x cubed minus 7 cubed. So there's going to be a formula you need for that. I wrote down your formula for the difference of two cubes and the sum of two cubes. For the difference of two cubes, you have x cubed minus y cubed equal. Now notice if you have x cubed minus y cubed, you have to have x minus y there. And then the rest of the terms are positive. You have x squared plus xy plus y squared. Now if you were to have the sum of two cubes, you have x cubed plus y cubed equal x plus y. And then for the middle term, you have to switch to negative. So you have x squared minus xy plus y squared. Okay, so before we go any further on this, I want to save you some time. So what I did is I printed the view and example. And on this particular one, it gave you x cubed minus 64. Well, since it's to the third power, you should just go ahead and say third root of 64, and you get 4. And that's the same as saying 4 times 4 times 4. This whole first page is about doing your potential zeros, then graphing it, finding that it's 4. Now, from there on, it's going to be good, but, those first steps are really not necessary. What you would do after that is you would plug in 4, see that you have a 0 remainder, which means it is a 0, and do your synthetic division to find your irreducible term, which would be based on the 1, 4, and 16. So that's going to be the 1, 4, and 16 are the coefficients or numbers. So you have x minus 4 times that. So you're going to have to do synthetic division. Then from there, since you can't factor it, you have to use the quadratic formula. and then from there you just got to keep on going. You're going to end up having a negative underneath the square root sign, and that's where you figure out your negative or your imaginary number. And then, it's plus and minus. And then from there, you're going to have to put it in this form. Okay, so let's do that on ours. So what we do is we know it's 7. And so we're going to do 7. This is our synthetic division step. And it's x cubed plus 0x squared plus 0x minus 343. So on this one, we've just put a 1, 0, 0, negative 343. So now we're doing our synthetic division. Bring down the 1, 7 times 1 is 7. Bring down the 7. 7 times 7 is 49. Bring down the 49. And 49 times 7 should be 343. So 49 times 7 is 343. And then you get a 0 remainder. Now, because of that, we put our 49, and then the 7 had to be the linear part, so we have 7x, and the 1 had to be the x squared part. Okay, so now we're to that step. So what that meant was we had x minus 7 times x squared plus 7x plus 49. Now the problem is this part we need to do the quadratic formula. Which is the negative b plus or minus the long square root of b squared minus 4ac all over 2a. So the a is 1 because it's the number in front of the x squared, the b is 7, and the c is 49. So this would be negative 7 plus or minus the long square root. 7 squared is 49, minus 4 times a, which is 1, so I don't write it, times c, which is 49, all over 2a, which is just 2 times 1. So this is negative 7 plus or minus the square root. This part I would just type in the calculator. So we've got 49 minus 4 times 49 is negative 147. All of that over 2. So then what that means is that it's negative 7 plus or minus I square root of 147 over 2. Now what I'm thinking about is if you add your numbers, 1 plus 4 you get 5, 5 plus 7 is 12. What that tells me is this is divisible by 3. What I want to know is if it's divisible by 9, because we need to simplify our square root. So we do 147 divided by 9. That didn't work. Before I go any further, I want to back up to what I said earlier. The difference of two cubes was this, and if you want to skip the synthetic division part and just use that, you can, because we said that you'd have x squared, and then you'd flip your sign from negative to positive, and there's your plus 7x, and then your 49. So if you want to skip that step to get to right there, you can. So with this, since that cannot be reduced anymore, we would have the first part, which is x minus 7, and then the second part is x minus it's really x minus a negative, so x plus 7 halves plus or minus I square root of 147 over 2. Now you may be saying, well, hey, that doesn't match. I see a lot of the similar questions on this have the square root of 3 on there, and I don't believe it. See, we're completely right with the x plus 7 halves, and the part that it's like we're not sure about is 7 square root of 3 over 2 equivalent to that? I don't think it is, but I think the key is wrong. So 7 halves square root of 3 is this, and square root of 147 is that. They're not the same thing. That's interesting. What if I did this one times 2? Then you get it. Okay. So, just thinking this through. So if we just called this part 7 square root of 3, then it would be equivalent. That's where their error was. So because of that, I'm just going to have this question skipped. I'm going to stop the video and then I'll continue with that.